Final video for Monday. Chapter 25, Section 1. We're going to talk about stars. Now, you'll remember early on, we voted on a chapter, and Chapter 25 narrowly beat out, I think it was Chapter 11, Volcanoes. So we're going to talk about stars today and kind of what they mean. It's important. Listen to the words. If you want to get down the notes, you can. But if you want to use these and go back and watch them multiple times, they will be up there for eternity. You can do that. So, let's talk. Constellations. When you look in the night sky, you see constellations. They're a pattern of stars in the sky. Now, with our constellations, we don't really pay that much attention to them. If you ever got a chance to go to the planetarium, oh my gracious, they'll show you them all. But you have to think how dark it used to be at night and the wonderful display it was. We can't do field trips this year, so we won't get to see that. But they looked and found these big stars, and they drew, and they used their imaginations, and they made pictures. You can kind of see, this is a person with his hunting bow, and he got his belt, and then he's got his kilt. All right. There's other ones like Taurus, which is the bull, Gemini, which is the dragon, Canis Major. All right. This is really what they were thinking when they drew these constellations. Ursa Major, it has one very big specific, one very big specific thing. That means Big Bear, but do you see the Big Dipper within Ursa Major? All right. These are ones that you would see in the southern hemisphere. Orion we see in the wintertime, and there's Orion's belt, which is very well known. Perseus, maybe if some of you have read some Greek mythology, you'd know that. There's Ursa Minor with the Little Dipper hanging out there. All right, Draco, which is the dragon. All right, all these are things that they would see, and they tracked these. All right, here's really what they were seeing when they saw that. We can see this is what it looked like, and they called that Capricorn. Scorpio was this group of stars, and the gases and the dust behind them used to be more prevalent, so they used their imagination, and they made more things visual. All right, so constellations are patterns of stars in the sky. All right. We won't be asked to identify any, but to know they exist is kind of there. Now, circumpolar. Circum kind of sounds like a circle, doesn't it? And that's exactly there. Why circumpolar constellations? Well, they seem to circle Polaris in the night sky. Polaris is the North Star, and because of the way Earth revolves around the sun, these stars seem to circle Polaris in the night sky. March, June, September, December. When you look up and find the Big Dipper, it will look different or at different angles in different months of the year. All right? Right now we're in September, so you'll see it flat and out on the northern horizon out there. As in December, it's pointing down. March, it's dumping everything on us. And in June, it's vertical like this. All right? So, they seem to circle Polaris, that North Star, because Earth revolves around the sun, which means it goes around in an orbit. Okay? Now, side by side, we're going to be comparing things. The brightness of stars. Apparent magnitude. Absolute magnitude. Usually we go out to the hallway and try to have a big discussion. Maybe we can do that another time. Or you may want to search apparent magnitude versus absolute magnitude. Okay. Apparent magnitude is the measure of the amount of light received on Earth. The light that appears to us. All right. Now I need you to think about driving in the car with your parents at night. When a car is far away with its lights on, they don't look very bright. But as that car gets up closer to your car, think how the light tends to seem brighter. The lights didn't actually change in brightness. They just seem brighter when they're closer because it's not being lost to distance. So the apparent magnitude changed from when the car was far away, it didn't seem as bright, to when it was close, it seemed quite bright. All right. Absolute magnitude is the measure of the amount of light a star gives off. That's the actual amount of light. All right. We can measure that. All right. But it doesn't change. That car, the headlights were just as bright far away as they were close. It's just the distance affected the apparent magnitude. Distance does not affect absolute magnitude. Distance affects. Distance does not affect. All right. Example, Sirius and Regal are two stars. Regal has a much higher absolute magnitude. So Regal is actually a lot brighter, but it's very, very far away from Earth. Sirius is less bright. Its absolute magnitude, it actually gives off less light, but it is much, much closer to Earth. So, which star would probably appear brighter to us? Sirius. Because it's so much closer, its apparent magnitude is much brighter, the way it appears. Which star is truly brighter? Because it has a bigger absolute magnitude, it's Regal. Okay? So absolute magnitude tells which is actually brighter. Apparent magnitude, which appears to be brighter because of their closeness or farness from us. So let's think about this. And this is when we'd be in the hallway and we compare a few different things. We will try to get that in when you get back. If we are comparing three stars' brightness, and they are all the same distance from Earth. Hold it. Distance. Ooh, that's an important factor. Star A has the greatest absolute magnitude. Star B has the least. And star C is between them. So we know their actual brightness. A the best, B the least, and C the between. Which star has the greatest apparent magnitude? So which one appears brightest on Earth? Now there's one important factor I told you. They're the same distance. So if they're the same distance, your absolute magnitude, which is what it actually is, and your apparent magnitude, the way it appears, are the same. Oh. Let's see if this wording helps you out. Since distance is the same, then we will know the greatest absolute magnitude will also be the greatest apparent. And the opposite is true. The least absolute will also be the least apparent. Now, measurement in space. Very hard to do. We make measurements in light years. That's distance. Okay? Distance light could travel in 1 year is what a light year is. In 1 year, light could travel 9.5 trillion kilometers in 1 year. So when they say 1 light year, they mean 9.5 trillion kilometers. That's pretty far. So how do we measure that? It's not like we can go say, here, you take the tape measure out there and do that. They do that by measuring these great distances with something called parallax. Parallax is something that's very important. You probably want to go to figure 3 on page 727. All right? Parallax is like the tool. It's like the ruler. So what they do is they literally look at an object far away. Look at it with both eyes. Cover one eye and put your hand out over that object. Then switch to the other eye and watch how the object jumps or moves. That's the trick that they use to do parallax. Then they do a bunch of fancy math and how far the object moved when you went from one eye to the other or one position to the other can help us know the distance. All right? So parallax is the tool and they do it by looking at the same object from two different points of view and then measuring the change, and they can get the distance. Now, star properties. We're going to talk about colors. Color tells us the temperature of the star. The hottest stars are purple to blue. Probably going to focus on the blue more. And the coolest stars, believe it or not, are red. Now you can see that as they transition, blue to green to yellow to red, orange to red. There's the group. But I'm going to give you blue stars are the hottest. Seem to make a big deal about that. Red stars are the coolest. You may want to remember that. So we go from blue-white, hottest, to green, to yellow, to orange-red being the coolest. Or if you want to think the other way, orange and red are the coolest, to yellow, a little warmer, green and blue-white. Now think of our sun, yellow. So it's about an average heat star. It's not really hot like the blue ones. It's not really cool like the red ones. We're about an average star. All right, ladies and gentlemen, your favorite slide. See you in a bit.